and here we will try to look into other aspects, that complete solidification in welding process, that complete diffusion in solid and liquid state. Here you can see that we assume that the material, the complete diffusion in the solid and liquid, the composition we choose in such a way that there is a complete diffusion in the solid and liquid state. So, that means if F s and F l actually represent the fraction of the solid and the liquid state, then it according to the conservation of the solute, this should be 1, F s plus F l should be with respect to 1, and if we look into that figure represent that the fraction, solid fraction and liquid fraction, it starts from 0 and gradually increasing to 1, and there is a transformation that happens during the that solid is it's a solid grows from the liquid phase, and that means from liquid to solid phase, and when in that direction the solid phase is gradually consuming the liquid phase. So, that total volume, total fraction should be 1. Now, graphically you can see that at any point, so this is the solid fraction some part and some part is the liquid fraction. So, this is the liquid fraction, this is the solid fraction, and C0 is the initial composition of the initial composition of the solute. Now, here at any point, here is the Cl liquid content, and this point represents the Cl and this the solid content, that means concentration of the liquid phase and concentration of the solid phase here in this case. Now, Fs into Cs and Cl into Fl basically represents the amount of the solute in the solid and the liquid phase. So, that total area with respect to C0, if you see the total area with respect to C0 is basically Fs into Fl into C0, the area represents, and which is corresponds to the amounts of the solute in the solid phase and amount of the solute in the liquid phase. So, that means it is equal to the area occupied by the solid phase plus area occupied by the liquid phase. So, that total content should be equal to the with respect to the C0. So, Fs plus Fl is simply 1 according to the solute conservation, and that means it is equal to C0. So, from this equation we can easily find out by applying the lever rule what is the solid liquid fraction and what is the solid fraction in this case. And of course, composition of the liquid also can be represented Cl C0 in terms of the K also, because K actually represents the ratio of the Cs by Cl. That means liquid solid content and the liquid content of this. So, in terms of the K, so here we can find out the Cl equal to in terms of the C0 fraction of the liquid and K in terms of K, and as well as the in terms of the fraction of the liquid we can write all these things. So, that is in this way we can represent the changes, the fraction of the solid and liquid during the transformation from the solid phase to liquid phase specific to the in case of the binary alloy system. Now, if we look into that, during this solidification process, the different types of the grain structure we can expect. Normally, one is that equiaxed kind of grains, that in this equiaxed kind of grains, if we see that equiaxed grain, if we consider the pool of the molten pool within the container, then the surface actually acts as a heterogeneous nucleation process. So, along the surface we can find out the almost equal size of the grains. So, crystal grows almost equally in all the directions, and that is the commonly found out in the adjacent to the cold metal wall. So, around the cold wall this there is a formation of the equiaxed grain structure. Similarly, we can find out the columnar grain structure. It is basically long and very thin, created under the steep temperature gradient. So, temperature gradient, high temperature gradient is oriented on specific direction, and that actually driving force make a columnar type of the grains. So, definitely columnar type of the grains is relatively slow as compared to the EQX type of grains, because EQX type of grains more or less actually happens throughout the whole throughout the surface, is almost at the same time. And another point is that columnar grains actually grow perpendicular to the surface, and entirely it depends on the, definitely this columnar types of the grain, it depends on the directed temperature gradient or high amount of the temperature gradient in specific direction. So, this easily form kind of grain structure normally we observe in the solidification process, and here we can find out that other type of binary alloy system, but here no solid diffusion and complete diffusion in liquid we generally observe, and one case is the no solid diffusion and limited diffusion also observed. So, in that case the behavior of the solidification becomes more complicated. So, here these two types of the solidification behavior is beyond our scope. Now, if you look into the what are the different types of solidification modes. So, during the solidification of a pure metal, the solid liquid interface is usually planar type thing. So, there is a front moves in say making like a plane. So, that is the one type of mode, but normally for an alloy system the mode of the solidification in the solid liquid interface can be the planar type of, it can be cellular, it can be dendritic type of the mode depending on the solidification condition and the material system involved. So, we will try to look into the different types of solidification mode generally observe these things. So, first one is the planar mode. So, that solidification front exactly moves making a plane and gradually moves. Cellular, there is a breaking of the planar mode and it can make a kind of structure like looks like a cell kind of structure. So, this is the cellular type of solidification modes. Another third is the columnar dendritic type structure. So, its the growth is a kind of columnar one direction, but the dendrites forms is a primary dendritic, secondary dendritic arm can also be formed. So, this is the typical columnar dendritic type of structure may also solidification mode can also be observed. Another is the EQX dendrite. So, of course, the dendritic structure exists within the one grain, but there are several positions almost equal size of the grains exist within the each grain. There may be the development of the columnar type of the dendritic structure, maybe the dendritic structure observed within the EQX structure. So, these are the typical solidification modes we normally observe, but if we look into that, here solidification and welding, but to analyze these things, that little bit the quantitative analysis of the solidification we can look into that constitutional supercooling.